two-dimensional kinematics. So one of the most important parts of understanding how to solve these problems is taking into account what's happening in the horizontal direction. So as a projectile travels through the air, and we say it's traveling through the air, but in actuality we are ignoring air resistance, the horizontal component of velocity doesn't change. And the reason that this is the case is because there's no horizontal forces acting on it. So, in the absence of horizontal forces, and this includes air resistance, there are no horizontal net forces. And we know that if there's no net force, that the acceleration has to be 0. But keep in mind, this is only in the x direction. In the y direction, the acceleration on Earth is going to be 9.8 meters per second squared down. Now notice I didn't say plus or minus because that depends on what we decide to call positive, whether we call that up or down. So let's look more closely at a projectile that has been launched off of a cliff and lands at some other height below the height that it started from. So if we look at the y velocity, this is the upward component of the initial velocity. And this, our x velocity, is the horizontal component of the initial velocity. And as it travels up, we have a net force down, so that means there's going to be a downward acceleration. When we have a downward acceleration and an upward velocity, the object slows down. So its Vy is going to decrease. It's going to decrease so much by the time it gets to the top, the Vy will have become 0. When it starts to head down, the velocity is down and the net force is down. So that acceleration down and velocity down means that the velocity is going to increase, but in the downward direction. That's going to continue. When we get to the point at which it's even with the launch point, the Vy here is going to be equal in magnitude to the V0y over here. And as it continues to fall, this Vy is going to increase more and more until it hits the ground. So these are all our Vy components. But the x component remains the same. So as it travels through the air, our Vx is remaining the same. And that's going to be crucial when we go to solve the problems. So that's our Vx, this is our Vx, 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 and so on. The actual velocity is the resultant of these two, and that's going to be the velocity along the parabolic trajectory. So again, in the y direction, the acceleration is down, and the x acceleration is 0. That means that the x velocity is constant. Let's go ahead and solve a problem. Let's say we have a projectile that is launched at 100 meters per second at an angle of 30 degrees to the horizontal. We have 3 questions to answer. How high does it go? How far does it go? And what's the total time during its flight? So the first thing that we can look at is that this velocity by itself isn't what we're going to use to solve the problem. We're going to break it up into x and y components. So the first thing we need to do is figure out what is this v0x and this v0y. So we have a right triangle here. So our v0x is going to be the adjacent side, so that's going to go with cosine. So we have v0x equals v0 cos 30. And that's going to be v0x equals 100 times the cosine of 30. And that value comes out to 86.6 meters per second. Then we need to do the same for the y direction. That's going to be v0 sine 30, or v0y equals 100 times sine of 30. and that's going to give us a v naught y of 50. Now, before we can start to decide what we're going to fill out our table with, we have to decide what's positive and what's negative. So for this problem, I'm going to call up to be positive and down to be negative. So the first question is, how high does it go? And the height right here is going to occur when the y component becomes 0. So we're going to treat this as an up trip, where we're going to take our v naught y component and solve it from there to there, only vertical. So to do that, we're going to call this a y up trip. And we're going to say that v naught y is positive 50 meters per second. Our vfy, when it gets to the top, is 0 meters per second. Our acceleration is down, so that's negative 9.8 meters per second squared. And we're looking for delta xy. That's going to be the height. You could also call it h if you wanted to. That's our unknown. So the easiest way to do this is with a vf squared equation. And we can do 2a delta x. And that's going to give us 0 equals 50 squared plus 2 times negative 9.8 times delta x. And our delta xy, or our height, comes out to 127.6 meters. So, what is the time? Well, for the time, we're going to do a y total trip. So this will enable us to find the time from beginning to end. So our conditions are a little bit different. From here, we have our initial velocity is 50 meters per second, but our final velocity is the velocity here right before it hits the ground. Now, if it's launched at the same height that it lands at, our vfy is going to be the same value, the same magnitude, but opposite direction. So that's going to mean our vfy is negative 50 meters per second. Our acceleration is still negative 9.8, and the time is going to be what we're looking for. So we can do that as a vfy equals v naught y plus at. So that's going to be negative 50 equals positive 50 plus negative 9.8 times t, and that gives us a total time of 10.2 seconds. So we only have one question left to answer, which is, how far did it go? This is sometimes called the range. So now we're looking for the horizontal trip. So we're going to do this as an x total trip. And we know in the x direction from our v naught cos theta that our v naught x is 86.6 meters per second. And our acceleration, remember there are no net forces in the x direction, so that's an x acceleration, is 0. And we know from the last problem that our time is 10.2 seconds. So for a total trip, we can do delta xx equals v naught t plus 1/2 at squared. There's no acceleration in the x direction, so this drops to 0. And our delta xx is just going to be 86.6 times 10.2. And that gives us a horizontal range, or delta xx, of 883.3 meters. Now let's repeat this entire problem again, but do it as a derivation, so no numbers in this. And what we're going to solve for is the horizontal distance, delta xx, or the range. Now, because it's launched from a height that it lands at, its delta xy is 0. It lands at the same height that it took off at. That's going to be important, you'll see in just a second. So let's start out with our delta xx formula, which is v naught t plus 1/2 at squared. And we know that the acceleration is 0, so we can cross that out. Now, we know from before that our v naught in the x direction was equal to v naught cos theta. So our v naught x in this case is going to be replaced with v naught cos theta. And that's multiplied times t. So if we solve for t, we can isolate and get delta xx divided by v naught cos theta. So now we have an expression for time, which will help us sub in to solve for the y direction. So in the y direction, we can do a delta xy, and that's going to be v naught yt plus 1/2 at squared. And delta xy in this case is going to be 0. And what can we replace v naught y with? Well, that can be replaced with v naught sine theta, as we did in the last problem. And that's multiplied by t. Now, we can replace a with g, but remember, we called up to be positive and down to be negative. So if this is acceleration, that has to be negative, and I'm just going to move that negative sign to the outside. So that becomes negative 1/2 gt squared. So let's add this over to the other side. So we have 1/2 gt squared equals v naught sine theta t. And we can see that we have a t on both sides, so we'll cross out the squared and this t. And then what we can do is sub in for time, because we know what that is. We have an expression for it. So that's going to become 1/2 g delta xx over v naught cos theta. And on our other side, we have the same thing we had before, which is v naught sine theta. So what can we do from here? Well, we can cross multiply. So if we're solving for delta xx, we need to get this onto the other side. So that's going to become v naught squared sine theta times cosine theta. But let's also bring the g over, so that's going to put the g on the bottom, and multiply both sides by 2, which will get rid of the half and put a 2 on the other side. So that leaves us with delta xx equals 2 v naught squared sine theta cosine theta, all divided by g. Now, if you recall from math that 2 sine theta cosine theta is equal to sine 2 theta, then we can sub in sine 2 theta. We have a 2, and we have a sine theta and a cosine theta. So we can rewrite this as delta xx equals v naught squared sine 2 theta over g. Now, keep in mind, this is only true when delta xy is 0. If this was launched off a cliff, you can't use this formula. But I want to point out something that's interesting. When do we get our maximum horizontal range? Well, what's the largest value we can have taking the sign of a number? And that's going to be 1. Well, the sign of what is 1? 90. So sine of 2 times 45 gives us 90. The sine of 90 is 1, which gives us our max value. So the max delta xx for a projectile launched on a horizontal plane is going to be at its maximum delta xx when theta is 45 degrees. Here are a bunch of possible paths for various angles that projectiles are launched at. If we see here, at 10 degrees, our component of v naught x is very large, but v naught y isn't very large, so the time is very short, so it doesn't have a very large horizontal range. As the angle increases, we get more vertical components, so we get more time, and the projectile can travel further. Now, it turns out that there are complementary angles here. So launching at 60, although it will go higher, it will travel exactly the same horizontal displacement as at 30. And that's true for any two angles that add up to 90 on a flat plane. And as we saw in the last derivation, the maximum horizontal displacement occurs at 45 degrees. That's when the components v naught x and v naught y are equal. As we begin to go higher, the time of flight is longer, but the horizontal displacement starts to get shorter. And when we launch it at, I should have said 90 degrees, when it's launched straight up, we get the longest time of flight, we get the greatest height, but we get no horizontal displacement. So when xy is 0, delta xx max occurs at 45 degrees. And the complementary angles, 60 and 30, will produce the same delta xx, but the 60 degrees will produce greater height and greater time. The same for 80 and 10. Same delta xx, but different times. What would this look like if there was air resistance? Well, it's a perfect parabola if there's no air resistance. But if there is air resistance, v naught x starts to get shorter and shorter as it loses x velocity because there's a net force due to air resistance, so the path will run short. If we launch our projectile off of a cliff, then the horizontal range actually doesn't occur at 45 degrees. So you can see at 90 degrees it goes straight up and comes straight back down. And our angle down at the bottom here, launched perfectly horizontally, also doesn't travel very far. The 45 degrees will land at the same height, and that would be the maximum displacement if that's where it ended. But we actually get a further displacement when it's launched somewhere between 0 and 45 degrees. You actually have to do the calculation because it depends on the height of the cliff. But this passes this because it has a larger Vx. That Vx, coupled with the longer time, allows it to have a larger delta xx. So there's an interesting video on Mythbusters where they shoot a bullet out of a handgun, and the bullet travels in a parabola, but they take another bullet and drop it down. Both bullets hit the ground at the same time because they're both accelerating down at 9.8 meters per second squared. Just because a bullet is traveling horizontally doesn't mean that it's not falling. So let's say we wanted to solve a problem like this, where we have a 19.6 meter tall cliff with a horizontally launched ball of 10 meters per second. How far will it go? Well, the first thing we can do is use the height of the cliff to find the time of fall, because a ball falling straight down will take the same amount of time as a ball launched horizontally. So we can just do delta x y equals v naught t plus 1/2 at squared. Now, even though it's moving 10 meters per second horizontally, it has no up or down velocity. So at the moment it leaves the cliff, its initial y velocity is 0. So that drops out. So we say 19.6 equals 1/2 9.8 t squared. This gives us 4.9. That divided by this is 4, so the square root of 4 is 2. So how far will it travel horizontally? Well, we know that it's 10 meters per second. That's x information, and that's not going to change. So we can again say delta xx equals v naught t plus 1/2 at squared. And because there's no acceleration in the x direction, this drops to 0. So our delta xx is equal to 10 meters per second times 2 seconds, or x is 20 meters. But let's go ahead and do this as a derivation. So if we have our cliff, and the cliff has a height h, and it's launched with an initial velocity of v0, it travels the same parabola, but let's solve for xx. So we can go back, and instead of saying x0 equals v0 t plus 1/2 at squared, and instead of putting in delta xy, we can sub in the height. And our v0 y is 0, and we can sub in g for acceleration. Rearranging for the time, we get t is equal to the square root of 2h over g. So let's go ahead and do the other part of the equation, delta xx equals v0 t plus 1/2 at squared. And in this time, same as before, the x acceleration is 0. So our delta xx is going to be v0 t, which is just v0 times 2h over g. Finally, let's look at a very popular physics question, which is the monkey and the zookeeper. And the zookeeper has a gun that shoots a vaccine dart. And the question is, should the rifle be pointed above the straight line, at the straight line, below the straight line, if the monkey releases from the branch at the moment the gun is fired? So the gun goes off and the monkey starts to fall. Well, if the bullet is traveling along this path right here, this is what it would do if there was no gravity. But the bullet, we know, is falling away from that straight path at 9.8 meters per second squared down. Well, so is the monkey. So it's a bit counterintuitive, but you would want to point the gun directly at the monkey so that the bullet falls away from the straight line path at the same acceleration as the monkey. It will always hit the monkey, because if the dart was traveling at a very high speed, it wouldn't have much time to get away from this straight line path, but the monkey wouldn't fall very far. If the bullet was traveling very slowly, it would give the monkey more time to fall, but the bullet would have more time to fall. In any case, the monkey will still end up getting hit by the vaccine dart when it falls.